Sí. Okay, so hello again. Let's continue with the next speaker this morning. Is Natàlia Castellana from Barcelona, who is going to talk about local Gorenstein duality. Please.
Okay, thank you very much. Well, first I want to thank both Imma and Andy, the organizers, for all the effort and all the work they are putting on the organization of these workshops. So I really appreciate this, and I apologize that I've not been able to attend all the lectures that I wanted to, but life took on and it was complicated. Okay, so what I'm going to talk is a project, a joint work with Tobias Barthel, Drew Hart, and Gabriel Valenzuela. And the title, Local Gorenstein Duality, is what I'm planning to introduce in the first part of my talk. Okay, so first part, zero section, what's local Gorenstein duality? Okay, I'm a very unstable person, so I will start with unstable homotopy. I start with a topological space, so let X be a connected space, a commutative ring. And then when you take a course on algebraic topology, one of what you learn is that there are functors that go from topological spaces to algebra, which detect symmetries of your space in different ways. So one of the functors that you learn is cohomology. So you can take just singular cohomology in coefficients in a field, and what you obtain is a graded commutative ring. In fact, what you obtain is a graded commutative augmented K algebra in the case of a field. Originally you have a product, and the product is induced by the diagonal. For example, if you have coefficients in a ring, is a way to see it. So once you have a commutative ring, you land in the realm of commutative algebra, and you can ask yourself about different invariants and information that you can obtain from this ring just working in commutative algebra. For example, when you take all these techniques, there are invariants that you can associate to a ring, right? And these invariants, they can measure sometimes the finiteness of your ring. So the first thing you can ask is whether your ring is Noetherian, for example, right? So, and there is several properties that that you can try to compute or check on your commutative ring. So you can ask whether it's Noetherian. If it's Noetherian, then there are several invariants that measure this finiteness of your ring. You have the Krull dimension. So you look at the length of chains of proper ideals, prime ideals, and that gives you this Krull dimension. And you can also look at the depth. That means that you look at the maximum length of a regular sequence in your ring. So these two numbers measures somehow the finiteness of your ring. If these two numbers, they do not need to agree, but if they agree, then you define a class of rings. They are Cohen-Macaulay rings. Right? So Cohen-Macaulay rings are those for which the dimension and the depth coincide. I mean, you have this dimension defined in terms of prime ideals of you have the height of a prime ideal as the maximum length of a chain starting from 0 to this to your ideal, or you have the depth. And then when they coincide, you have Cohen-Macaulay. And then there is another notion inside Cohen-Macaulay rings, which are this Gorenstein property. So I'm going to say a few words about this. So so as I said, Cohen-Macaulay means the dimension and the depth coincide. So what's Gorenstein? So there are several characterizations of Gorenstein rings. Let me, one here are two which I just sketched it. The first one is, well, what's a Gorenstein ring of dimension 0? So a Gorenstein ring of dimension 0, so it's a ring which satisfies this story that ohms from R into KR as a, well, I'm sorry, here I moved to K algebras because that's what I'm going to focus later. So when these the ohms from R, K, R is of dimension 1, is K as a vector space. And then what's of dimension N? So it's of dimension N when you quotient by a maximal sequence, regular sequence, what you obtain is something of Gorenstein of dimension 0. So that's a way of seeing it. So somehow what this, naively, you can think of this like saying that if your K algebra is finite, Gorenstein means Poincaré duality. And when it's not finite, it has dimension N, means that you quotient by this polynomial subalgebra over which is free, and then what you obtain is a Poincaré duality model. They can be also characterized in terms of the X functors, right? So it's when you compute the X functors, as I wrote, RKR, they are all concentrated in 1 degree, which is degree N, and in this degree is K. Okay, so you can think of this in terms of this property of X functors, or sometimes for me in a more naively, when I think of in terms of cohomology algebras, I try to think of that the cohomology is free over polynomial subalgebra and the quotient is Poincaré duality. That's another way of trying to understand this Gorenstein property, right? So we have this chain of inclusions in commutative rings, and then the question that what I said before is that that if you have a K algebra, finite dimension of a K vector space, Gorenstein is essentially Poincaré duality. And then examples, I wanted to say some examples. Polynomial algebras are Gorenstein and Poincaré duality. And these are going to be somehow the main examples in which I'm going to do later. Right? Okay, so now the question is, when you are coming from topology, you have a topological space X and you compute the cohomology, and you want to see which property satisfies this cohomology ring. You would like to detect these properties, but without the need of computing explicitly the cohomology. Right? So the question is, can we detect these properties, these invariants on the cohomology of X without explicit computations, and maybe using some geometry of the space X or some symmetries of the space X, which imply that the cohomology ring will have these properties, right? So I'm going to see some examples. If you have a finite CW complex over a field, then, and you take the cohomology over a field, well, the cohomology is Noetherian, it's just a finite, K algebra, it's finally generated, so it's of dimension 0, moreover. So it's Cohen-Macaulay, and in that case, they coincide the depth and the dimension. And then it's Gorenstein if only if satisfies Poincaré duality. So in that case, this Gorenstein property is reflected by this Poincaré duality in the cohomology. So if you have the example that I like the most is the one that comes from finite groups. So so an example of a CW complex which is not finite, there's a typical example you learn in an algebraic topology course is that you have, for example, real projective spaces, and then you take the colimit, or you have a spheres and you take the colimit, and then you have CW complexes which are not finite. That case is, for example, if you take RP infinity, this is the classifying space of BZ2. So, so if you have a finite group, you can associate to it a classifying space, BG. You can think of it as the classifying space for principal G bundles over CW complexes. But the point is of this space is that when you compute the cohomology of BG, this can be done in terms of G itself without the need of going through the space. I mean, that's group cohomology. So if you have a finite group, you can learn group cohomology from homological algebra, Or you can just think of it as the cohomology of the classifying space in terms of singular cohomology, for example, right? So there is these two ways of looking at group cohomology. From a more algebraic point of view, from the group itself, you don't need to know about classifying spaces to compute group cohomology, or from this more topological side. And one can take advantage of working in those two areas. So that's what happens in that case. So the first question we can ask whether the cohomology of a group is Noetherian, right? Another remark that, well, it will appear later, but when you start a group course on group cohomology, there is the very first example that you learn is to compute the cohomology of Z mod P, or the cyclic groups in general. And this is an example that can be done from scratch, I mean, from the definition. But then essentially the other examples that you learn about are built out of this one by using extensions or fibrations. But the very basic example that you compute from essentially the definition is the case of Z mod P. So the question is this Noetherian? So the answer is yes. And so let me tell you the technique, because that's something I will use later too. So there is several ways of showing that the cohomology of a finite group is Noetherian. Yeah, I didn't say from now on I will mainly focus on the case when I'm talking about a finite group, the field of coefficient will be FP. Right? So what's the technique? When there are kind of two ways to show that the cohomology of a finite group is Noetherian. I will focus on this one that's using unitary embeddings. So if you have a finite group, there is a representation of this group in a unitary group. You can take just a regular representation, and it's a monomorphism. And the idea is that you think of the group acting on itself by left or right multiplication. That gives you permutation representation of the group inside matrices. And that gives you a mapping to sigma n, and that's, then you can embed this into the unitary group. So this is a mapping to G into UN, a monomorphism, right? So if you have a group morphism and you take classifying spaces, you have a map between classifying spaces, then you have a map from BG to BUN. And the fiber turns out to be that's the G acts on UN by multiplication via the representation, and the fiber is this quotient of UN, which is a finite, it has the multiplicator of a finite CW complex by this action of G. So it's a finite CW complex, has the multiplicator of a finite CW complex, right? And there is a fibration of this form, right? And there are 2 points. The first point is to have such a fibration, and the other point is that the cohomology of the classifying space of unitary groups is well known, right? And it's a polynomial algebra. If it's a polynomial algebra, in particular, for example, it's Gorenstein, right? So you can approach the cohomology of BG by using the set spectral sequence. Because of the fiber is finite, the idea is that you can show that using a set spectral sequence arguments is that the cohomology of BG is finally generated over the cohomology of BUN. You can think of the map that goes from the cohomology of BUN into the cohomology of BG. You can think of the cohomology of BG as a cohomology of BUN module, and then using the fact that the fiber is finite, so in your spectral sequence you will have a finite number of files, right? So it will be 0 from some point on. You can show then that the cohomology of BG is finally generated as a cohomology of BUN module. But you know that the cohomology of BUN is Noetherian, and then if you have a map between ring homomorphisms, and as I written here, so if S is Noetherian, R is finally generated as an S module, then R is Noetherian. So that shows that the cohomology of BG is Noetherian. This is one standard argument. The other one, which it's using a transfer argument using a silo subgroup. That's the kind of the two techniques that you can use to approach the Noetherianist properties. I also wanted to show this technique because this technique also works for compactly groups because this is not so easy. I mean, like having the regular representation for a finite group, but there's a theorem, the Peter-Weyl theorem, which tells you that every compact connectively group admits a unitary embedding. And then the same argument goes through, and you can show that the cohomology of BG, where G is compactly, is also Noetherian. Okay. Oh, sorry. There's a question: Poincare duality between what two? I mean that the cohomology is a Poincare duality algebra. It's okay, so so this is, and that could be called kind of an ascent technique. So you use the Noetherianness of UN, of the cohomology of BUN, to infer the cohomology of BG. Right? This is this thing that goes back to work of Benkov, if I'm not mistaken. But now I want to show you another technique, which is a descent technique. So in some conference, there was some point there was some discussion whether ascent is really ascent or descent, and I mean, depends on how you look at it. Okay, I want to also mention another technique which is used in group cohomology, which is a descent technique to go into subgroups. Right. So the technique is the example I want to show you is it goes to Quillen. Once you know that the cohomology of BG is Noetherian, you can ask yourself about these invariants, for example, the dimension. So I know it's Noetherian. Question: can I compute the dimension, the crude dimension, without the need of computing the cohomology explicitly? So is there any property of G, is any information in G which allows me to compute this dimension of the cohomology of G, right? And this goes back to the work of Quillen, and that's an example of a descent technique. So instead of using supergroups, we are using subgroups, okay? So what Quillen showed is that if you take all elementary abelian subgroups of G, you take the family of all elementary subgroups of G, we know explicitly the cohomology of elementary abelian subgroups. We know the cohomology of BZP. Then we know the cohomology of R copies of BZP. So it's, if P is equal to 2, it's polynomial. If P is odd, it's polynomial tensor exterior. So we have very good information in that sense. We know the crude dimension, for example, is the rank. We only need to look at it, and we know that the crude dimension is just the rank. Okay. So now you take your finite group, you look at all elementary abelian subgroups inside of it, and you can, when you have the cohomology of all of these, you can form a system. I mean, you have inclusions of elementary abelian subgroups one inside the other, and then you have conjugation. Some of those elementary abelian subgroups are related to each other because they are, one is subconjugate to another one by an element of G. Okay. And then you look at the inverse limit of the cohomology of these elementary abelian subgroups, and the indexing category is taking over inclusions and conjugacy relations in the big group G. Right? So what we are taking essentially is that you are taking tuples which are compatible. If you take tuples of elements in the cohomology of elementary abelians, which are compatible with respect to inclusions and conjugations. Okay? So what Quillen show is that the natural map that goes from the cohomology of BG into this inverse limit is an F isomorphism. An F isomorphism means that the kernel and the co-kernel are nilpotent, essentially, right? So if the kernel of the co-kernel are nilpotent, you can use this F isomorphism to compute the spectrum of prime ideals for the cohomology of BG in terms of of the spectrum of prime ideals for the cohomology of elementary abelians, right? So the spectrum of prime ideals is completely determined by the spectrum of prime ideals for the cohomology of elementary abelians, for which we know a good knowledge, and how they glue together using inclusions and conjugacies, right? I wrote it in a very naive way, but there is a very explicit formula. So this is called Cullen's stratification theorem because it tells you exactly how the primes in cohomology of VG are very precisely detected in a certain elementary abelian subgroups. So this is a descent technique in the sense that we know information about subgroups, and then we just, this completely determines the information about the cohomology of VG in that case. In particular, that tells you that the dimension is just the maximal, take all ranks of elementary abelians at the maximum. Right? That's if instead of taking, just make a remark aside, so if it's instead of taking all elementary abelians, you take all P subgroups, right? So you take all P subgroups, then this map is an isomorphism, and this is the stable elements formula. So the cohomology of VG is completely determined by the cohomology of its P subgroups, always in the coefficient, the field, the coefficient is FP always, right? When I'm talking about the finite group. So if instead of elementary abelians, you just don't restrict and consider all finite P subgroups, then you get an isomorphism, and this is the stable elements formula. If you just restrict to, and that was proved by Evans, I think that goes back to Cartan, Ellenberg, and Evans, and if you restrict only to elementary abelians, what you obtain is an F isomorphism. What you cannot see is the nilpotent elements within the kernel and the co-kernel. But this is enough to determine the spectrum of prime ideals, homogeneous prime ideals, and then you can compute the dimension of the cohomology of VG, the Krull dimension. So this is an example, of descent technique. Okay, so I want to focus, but now what we know the dimension, we can ask whether this is the cohomology of VG is Cohen-Macaulay, right? I mean, we go through this chain of inclusions. And so there is a theorem in the 90s by Benson and Carlson that says that the cohomology of G is Cohen-Macaulay if only if the cohomology of G is Gorenstein. The cohomology of G does not need to be Cohen-Macaulay. Yeah, I mean, you can, I think there is an example in this paper, I think it's semi-dihedral groups, if I'm not mistaken. There is an example of a cohomology of a finite group, which is not Cohen-Macaulay. But if it's Cohen-Macaulay, it's automatically Gorenstein. So naively, just say if it has a polynomial subalgebra such that it's free over this polynomial subalgebra and finite, automatically this quotient will have Poincare duality. That's essentially what it says. So, well, to understand this phenomenon, I want to say a few words about why this happens, the strategy that Benson and Carlson follow. Okay, so there is another way of detecting the properties of being Gorenstein and Cohen-Macaulay, which is by using local cohomology factors. So what's local cohomology? So you start with a thin commutative ring and you take an ideal and an R module. So you find a functor, which essentially you look at the A torsion in your module. So you are looking at the elements in M such that are annihilated by some power of this ideal A. Right? This is the A torsion submodule of M. Right? So this functor that goes from the category of R modules to itself is self-exact, and then you can take the right-derived functor, and these functors are the local cohomology functors, right? So they are the right-derived functors of the A torsion functor, right? Then, so what the point is that you can characterize these properties, Cohen-Macaulay and Gorenstein, by using these functors in the following way. So if you have an Ethereum commutative local ring, now I will remember that I will specialize at some point in cohomology of connected spaces that they will be local in that sense. So if you have an Ethereum commutative local ring of dimension D, R is Gorenstein if only if its Cohen-Macaulay plus some X functor is concentrated in 1 degree. And if only if, and this is the characterization in terms of local cohomology, you take the maximal ideal M and you take the local cohomology functor at this ideal. So it's Gorenstein if only if this functor is concentrated in exactly 1 degree. In the degree, this degree is the degree of the dimension as an Ethereum ring. And the value in this degree is the injective Hall of K as an R module. So that's a way of characterizing Gorenstein in terms of these local cohomology factors. Right? You look at the local cohomology at the maximal ideal, and then you check that it's concentrated in 1 degree, and then it has some value. These local cohomology functors, in fact, they if R is Noetherian, they take values in a range that goes from the depth to the dimension. Away from this range, they are 0. So if it's concentrated in just 1 degree, then you got Cohen-Macaulay. And if the value in this degree is this injective Hall, then it's Gorenstein. So, this is the characterization that it's used. And then what Benson and Carlson did was to construct a spectral sequence. Now, their paper works in homological algebra, and they construct a spectral sequence that goes from the local cohomology of the cohomology of G and converges to the homology of G. So it's a kind of duality, right? So they construct this spectral sequence. And now, once you have this spectral sequence, which is the core of the work, what happens is that if the cohomology of G is Cohen-Macaulay, we know that the local cohomology functors, they are concentrated just in 1 degree, which is the degree in which the depth and the dimension coincides. Right? And if it's Cohen-Macaulay, then this spectral sequence degenerates to 1 line. And then we know the target. So what it says that these local cohomology functors apply to we just computed the value of these local cohomology functors for the cohomology of G. And it turns out that's the dual. And this turns out to be the injective Hall of FP inside the cohomology of G. Then in that case, this is Gorenstein, right? So the main core is just to have this spectral sequence at hand. Because once you have this spectral sequence, Cohen-Macaulay implies that this degenerates, and the target, it tells you that you have this duality. Right? So that's what I wanted to point out. So one can ask at this point how general this spectral sequence is, because this is constructed in homological algebra specifically for the cohomology of G in this original paper. Right? Okay, so let me tell you a bit about how this phenomena can be understood in a more general context. So there are 2 questions. How general is this phenomena? Can I take the cohomology of a topological space X and play a similar game? And what happens at other primes? I mean, here we are focusing in the maximal prime ideal, right? So to understand how this works, so we need to take an intermediate step in between unstable homotopy theory, I mean connected space, and going directly to the algebraic wall, which you have the cohomology of X, the commutative algebra, and the step in between will be a stable category, the pure step. And what you consider is, given a connected space, you can consider the geometric cochange of this space. This is just a function spectrum from the suspension spectrum of X into the Eilenberg-MacLane spectrum for K, which is the coefficients. Right? And then if you take the homotopy groups, the stable homotopy groups of this spectrum is just a cohomology. The homotopy groups of this spectrum of geometric cochange is just a cohomology. So we just stop in between, right? And this is a ring spectrum. And the reason that it's a ring spectrum is what I said at the very beginning for the cohomology. X is a topological space and you have a diagonal. You can go from X to S cross X. You have the diagonal. And then since the Eilenberg-MacLane spectrum for K is a ring spectrum, you use the product to construct the product for the cochange. So it's not only a spectrum, but it's a ring spectrum, right? Okay. So we'll try to rewrite all these properties of Gorenstein in this setting of ring spectrums. Okay, remember I just recalled the definition that the characterization, the last characterization, there are a lot of characterizations of Gorenstein ring, but this one in terms of the local cohomology. So the first notion of what's a Gorenstein ring spectrum appears in the work of Dwyer, Greenlees, and Iyengar, this duality in algebra and topology. And you have a ring spectrum and a map from which is it's augmented from R to the Eilenberg-MacLane spectrum for K. K, in my case, it will be FP. You can keep in mind that will be FP or Q. I will say something about the rationals later. So this morphism, in fact, is Gorenstein if, well, when you look at the ohms from R, the ohms as R modules, I mean, the HK is an R module via just the map. Right? So when you look at the map, the ohms as in R mod in the category of modules over this ring spectrum, these ohms from R as R modules from HK into R turns out to be just a suspension of the Eilenberg-MacLane spectrum of K for some D. And D is the shift, that will be called the shift for this ring, Gorenstein ring spectrum. It will be a Gorenstein ring spectrum of shift D. If we have this equivalence between these ohms as R modules from HK to R, with a suspension of K. Right? This kind of mimics, I mean, the definition instead of the X functors. You can think of these ohms as derived ohms, right? And then this mimics this definition in the middle, the part for the X. Sorry. Then the point one has to keep in mind is that the ring being Gorenstein does not imply that it's homotopy groups which are going to be a ring, a commutative ring. So does not imply that these homotopy groups are Gorenstein in the algebraic sense that I just described. You can have a commutative ring spectrum which is Gorenstein in this sense of Dwyer, Greenlees, and Iyengar, but the homotopy groups are not. Right? So an example is provided by Greenlees itself in one of his papers. You can take RP2 and you can take coefficients in Z mod 4, and then the ring is Gorenstein, but the cohomology is not. Okay, so that's something that we have to be in mind. So that means that if the cohomology of the homotopy groups of the ring are Gorenstein, it means that you need some more structure apart than just having that the ohms are some suspension of the Eilenberg-MacLane space of K, right? So what we are trying to find is some, if we want to mimic the characterization on the left-hand side, the one on the left-hand side, we need some spectral version of local cohomology, right? So something that we can find a characterization of some Gorenstein property in terms of local cohomology. Okay, so that's what I'm heading to. So if we have an augmenting K-algebra spectrum R, you consider the stable category of R modules. You can say that a module is K-cellular if it belongs to the localizing localizing category generated by K. When I write K, I mean that should be the Ellenberg-MacLane space for K. So inside the category of R modules, you take HK, the Ellenberg-MacLane spectrum for K, and you can look at the localizing subcategory generated by it. So, and you say that the spectrum is K-cellular and R module spectrum is K-cellular if it's in this localizing subcategory. So the inclusion in this, the inclusion of log K inside this mod R is, the inclusion of cell K in mod R has a right adjoint, and this is the cellularization factor, right? So there is a factor that goes from mod R to mod R, it is cell K, which gives you the K-cellular approximation of a module M, right? So, and cell K of M belongs to this localizing subcategory generated by HK. So, so there was in the talk of Drew Hart on Wednesday, he described how these localizing subcategories and thick subcategories can be classified by stratification theorems in many situations, right? Using some support theory that will appear a bit in a bit. Yeah, for example, and then what's the relation of these functors that I just described, this cell K with local cohomology? Well, there is a particular instance, is that if you have a local Noetherian ring, you take the Ellenberg-MacLane spectrum of this local Noetherian ring, and then a module. It turns out that the homotopy groups of this spectrum, cell K of HM, is just the local cohomology at the maximum ideal for M. So you can think of this cell K as kind of a spectral version of the local cohomology of the maximum ideal, right? And then that leads us to another definition of a Gorenstein property, right? You can say that your ring is Gorenstein if, let me go back to if, now we look at the local cohomology characterization, if these functors, cell K, are, well, certain suspensions of a special module which play the role of this injective Hall, right? Okay, so the definition that's due to Greenlee says that you have an augmented K-algebra spectrum. We say that R satisfies Gorenstein duality, so we added the duality in the terminology. We satisfies Gorenstein duality of sheaf A if, and this mimics this last characterization I wrote. So cell K of R is equivalent to a suspension of this K RK, right? And that, let me just go back to the previous, yeah, so that mimics exactly this characterization here, because in that case, this injective Hall is just K RK, the ohms, the dual. So this is the way of trying to give a spectral version, in some sense, of this Gorenstein property. So we say that R satisfies Gorenstein duality of sheaf A if we have this equivalence between this functor, cell K of R, which it mimics this local cohomology of the maximal ideal, and a suspension of this K RK, which mimics this injective Hall for K in R. Okay, so, and in this situation, then the work of several people, but I think essentially it's Greenlee, Liubexnik, and Dwyer-Greenlee-Iyengar, which says that if the homotopy, if the homotopy groups of R are Noetherian, and then when I say a spectrum is Noetherian, I mean that the homotopy groups are Noetherian. When I say a ring spectrum is Noetherian, I mean that the homotopy groups are Noetherian. So if you have the homotopy groups of R are Noetherian, and R, this augmentation satisfies Gorenstein duality, and then there are some technical hypotheses which for nice spectrum are always satisfied. There exist spectral sequences such that starts with the local cohomology at the maximal ideal for the homotopy groups of R and converges to the homotopy groups of a suspension of this OM-K-RK, the morphisms from R to K as K modules, right? How this relates to the Benson-Carlson spectral sequence that I mentioned before, I mean, it's just the Benson-Carlson spectral sequence when you take for R to be co-chains on BG. If R are co-chains on BG, then the homotopy groups is the cohomology of G, and the target, and you take coefficients in FP, and the target is just the dual, right? So you have the OMS KRK, and then you converges to the dual with the homology. So in the case in which R is the cohomology, in which R is co-chained, is geometric co-chains on BG, then this spectral sequence specializes to the spectral sequence that Benson and Carlson constructed in homological algebra in their paper. So there is a spectral version of this spectral sequence, right? And we know. So for example, in that case, what happens is that if these homotopy groups, I mean, of R are Cohen-Macaulay, we can play exactly the same argument we played before for BG. So if these homotopy groups are Cohen-Macaulay, then these local cohomology functors are concentrated in a single degree, the spectral sequence collapses, and you know that the value is this injective which coincides with the target, and then you have a similar statement that if the homotopy groups are Cohen-Macaulay, then they also Gorenstein. So you can play, once you have this spectral sequence, you can play the same game, and you obtain a Benson-Carlson type result, saying that if the homotopy groups of this ring spectrum are Cohen-Macaulay, then automatically will be Gorenstein, right? Using the characterization of Gorenstein in terms of these local cohomology functors. Okay, so this somehow answers the first question about how general is this framework, this spectral sequence of Benson and Carlson. So we have a more general framework, which is this Gorenstein duality K algebras, right? And the second question is, well, what about other primes? We have been only working at the maximum on one prime, which is in this local ring at the maximal prime. So what happens at other primes? So for other primes, you need also spectral version of what's the local cohomology for other primes. Okay, let me just go back for a second here. So in that case, we constructed this functor cell K, which was like the spectral version of the local cohomology of the maximal ideal. Okay, the question is what happens at other primes? So is there some functor such that the homotopy reproduces these local cohomology functors constructed in algebra? So, and yes, there are such functors. These functors already appear in the talk by Jerome Scherer, by Drew Hart. Sorry, I was checking the chat to see if there was some question. So by Drew Hart on Wednesday, because these are the functors which define these support theories. And then if you have a prime ideal, homogeneous prime ideal in the homotopy groups of your ring spectrum, then there is a functor which goes from R modules to R modules, which is exactly spectral version of these local cohomology functors. What I mean is that in that case, what you have is a spectral sequence. So you have a spectral sequence that goes from the local cohomology supported at this prime applied to the localization at this prime of the homotopy groups of M and converges to the homotopy of these gamma functors. Okay. So it's not in the case of a maximal ideal, you had a more direct way because of identifying that case. You have a spectral sequence that goes from the local homology at the prime of the homotopy and converges to the homotopy of this spectral version of the local homology. Okay? And these are exactly the same functors that appear in the talk on Wednesday to define support theory. Okay? And then you can just use these functors now to construct, give a notion of Gorenstein duality at different primes. The definition of Gorenstein duality we just saw is just focused on a single prime, on this maximal ideal prime. And the definition of this is appears in a work. Appears in a work of. Well, it's a subset of the co-authors of this work, and it's a complement of myself. So it's Barthel, Har, Valenzuela. So in a previous work, they defined the notion of local Gorenstein duality. And a ring spectrum satisfies local Gorenstein duality of shift A if, and then what you obtain is a definition that if you take the maximal prime ideal specializes to the previous ones, but it goes through all primes. So for each prime of dimension D, the dimension is the co-height of the prime. At each prime, the values of these local homology, spectral local homology functors are defined to be a suspension of a spectrum, and this spectrum is a spectrum whose homotopy is the injective whole of the homotopy groups of R quotient by P. So let me go again. So Gorenstein duality is about the local homology functors having a very specific form, right? Concentrated in 1 degree and being the injective whole for the maximal ideal. So if you take another prime, then you look at these functors, gamma PR.
Sí, hazle a José Antonio ahora. Estoy escuchando a Natàlia en una charla.
So these functors, gamma PR, so they are suspension A plus D. A is the shift in the definition, and D is the co-height of the prime. So if we are working at the maximal prime, the co-height is 0, right? So this is the suspension, and what you have on the right now is a spectrum, but this is a spectrum such that its homotopy groups are the injective whole of the quotient of P star of R mod this prime. So just look at it and imagine that P is the maximal ideal. In that case, you are looking at the injective whole of the field, and it specializes to the previous definition. Right? So the one thing that one observes in this definition is that it's telling you that this local homology functor supported at a prime that define these support theories. If your ring satisfies this property, the homotopy of these functors are completely determined by the ring itself. So you take the homotopy groups of R, you quotient by the field, and you take the injective whole. So it's completely determined by the homotopy of the ring. So this is the definition of a local Gorenstein ring in the sense that it goes through all primes, not only involves the one prime as the previous definitions. Okay. So let me just make a remark here. Yeah. So, which is a bit of what I was saying. If K is a field and you have a co-connective commutative augmented K algebra, and you look at the homotopy groups of these functors which appear in the previous definition of Gorenstein ring. Recall that Greenlee's definition of Gorenstein ring was only about this here. So in fact, these homotopy groups turn out to be the injective whole of the field. So in that case, it specializes to this definition, when you take the maximal ideal, specializes to the previous one in this situation, right? Okay, so some consequences of having, okay, imagine that you know that your ring spectrum satisfies this local Gorenstein duality. What's this good for? Well, one thing I pointed out is that these functors are completely determined. These functors for support are completely determined from algebra, from the homotopy groups of the ring. But there are other consequences here at the bottom, that you have now a spectral sequence. And there is a spectral sequence that starts with the local cohomology of the prime P of the homotopy groups of R localized at P, and converges to this suspension of the injective hole of P star of R quotient P. This is just specializing on the spectral sequence that I described before. So that could be when you take the maximal ideal, that could be the analog of the Benson-Carlson spectral sequence for G. Right? And the other consequence is that you have a good knowledge of the homotopy groups of this support local cohomology at the prime P by just using the homotopy groups of the ring. So that's two consequences. Okay, so what we want to do? So what we want to do is we know examples of local Gorenstein duality rings, which are going to be our basic examples, as I tried to introduce or say at the beginning. So our, for example, BUN. BUN has a polynomial algebra. The cohomology is a polynomial algebra, so it's a very nice ring. And Poincare rings with Poincare that satisfy Poincare duality. Right? So the idea is that if I have a very few examples, how can I obtain more examples out of this? How can I construct more examples of local Gorenstein rings? How general is this property in some sense? So what I'm going to describe is, well, an ascent technique. So the technique I told you at the very beginning, that for showing that the cohomology of BG is Noetherian, that I have from a map from BG to BUN, such that the cohomology of BG is finally generated of the cohomology of BUN, and then I can obtain the Noetherianness of the cohomology of BG from the Noetherianness of the cohomology of BUN. So this is an ascent technique. So what we work in this project is also an ascent technique for local Gorenstein duality. Okay. So the ascent technique, I mean, this is one of the theorems. So the situation is the following. We have a finite morphism of augmented K algebras. Finite means that R is finite as an S module, and finite means that belongs to the thick subcategory generated by it. Right? So when I say finite, I mean that R as an S module is in the thick subcategory generated by S. Right? So if I have a finite morphism of augmented K algebras, I can consider this tensor. So these two are augmented into K. Then K can be viewed as an S module and as an R module via the augmentations. So I can tensor R and K over S. They are both S modules. Right? And assume that, well, both R and S are orientable Gorenstein. I will say now what I mean by orientable, or why it's the need of orientable here. So if R and S are orientable Gorenstein of shifts R and S. And then I have a condition on this Q that I described before. Q is in the thick subcategory generated by K. And then there is a technical condition, I will not say anything about it, which is that R and S to be DC complete. But this is the technical condition that will be satisfied for the examples I will tell you later. Okay, so if you have this hypothesis, then if S satisfies local Gorenstein duality, then R also satisfies local Gorenstein duality of shift R. I mean, this is one of the statements. And the idea, I mean, let me say something about orientable. So what I mean by orientable is a technical condition. I will not write the full thing, the full definition, but means that it's Gorenstein plus some extra property, which essentially is a condition which implies this equivalence I'm writing here, so that both R and K, from R to K as K modules, these two, they have the same cellularization up to a shift. That's this, what orientable means. So if you look at the right, you have like the dual of R. And it's a kind of, that's the reason it's called orientable. It has to be some duality. Yeah? And the point is that when a ring is Gorenstein, there are two functors which, two Ohm functors that can get an action of certain ring, and then you need this action to be the same. I mean, it's about some unicity of an action of a ring, and it's a very technical condition, but in practice, orientable will mean that both R and Ohm K are K, they have the same cell functor up to shift. That's how it's used in practice. Right? So this is the orientable part. And if you have a co-connective augmented K algebra, in fact, Gorenstein orientable will imply also Gorenstein duality. Right? So here, check that in my theorem, I'm not asking for R and S to satisfy Gorenstein duality. I'm only asking for the weak version, that orientable Gorenstein. Right? There are several versions of this theorem. This is the one I wrote, but then you can play along with applying conditions, just writing conditions on the morphism. There is a notion of a morphism F being relative Gorenstein. Essentially, it means that ohms from R to S as S modules is a suspension of, now I have to think, is a suspension of R. Yeah, I mean, there is a notion of morphism being relative Gorenstein that can replace one of those properties, 1 and 2. And there is also a version you can play along, and sometimes if you have Gorenstein, if the morphism is relative Gorenstein, then this Q will be also Gorenstein. So there are several versions, but this is the idea of the ascent technique, that you have Gorenstein duality for S, and then you want to infer Gorenstein duality for R, right? So if you think of the situation for spaces, that means that in the case of BG-BUN, that means that you have BG to BUN when you take cochains into reverse directions. So you have from BUN to BG, so from cochains BUN into cochains BG, and if you know that cochains BUN is local Gorenstein, then you will get that the cohomology of the cochains on BG is local Gorenstein, right? So these are some remarks, and then, as I said, there are some versions of this result, but they are more technical, so I didn't want to go through it. And then that consider assumptions on the functor or assumptions on Q. Right? Okay, so let's see to which examples we want to apply these these properties. So there are some examples of that coming from a space. So the goal will be to apply these techniques to fiber sequence of spaces, essentially. So if you have a topological space, you can consider the ring spectrum of these geometric cochains, which are this function spectrum from the suspension of a spectrum of X into HK, and then we will have some assumption in the background all the time when dealing with the spaces, which is what Greenleaf calls space being of Ellenberg-Moore type. So if we are working with a field of rational coefficients with Q, then we will assume that X is one connected. and if we are working with FP, then we'll assume that the fundamental group is a finite P group, right? That's this assumption will be in the background most of the time. So the idea is that if you have a fiber sequence of spaces from F to Y to X, that induces a map from a cochange. So you go from the cochange of X into the cochange of Y, right? And when your spaces are of Ellenberg-Moore type, what happens is that this Q I described in the theorem, that's going to be the tensor product of the cochange of Y with the Ellenberg-MacLane spectrum of the field as cochange of X modules. This can be identified, it's not just another module, but can be identified geometrically with the cochange on the fiber. So this is an important point, right? Because that means that if you have information on the fiber, you will have information about this Q, this module. Then, remember, let me go back to the theorem. Then one of the assumptions, assumption number 2, was about this Q, right? That it's in thick, the thick subcategory generated by the field. Right? So that means that if we want to apply these ascent techniques, we will need to have information in on the fiber of this the fiber of the map from Y into X. Right? So, well, let's first see some examples. Okay, so examples. So the first examples appear in the work of my 3 co-authors. If the homotopy groups of R are Gorenstein, then automatically the R satisfies local Gorenstein duality. You have a Gorenstein duality at any prime. And this is what they call a ring to be algebraically Gorenstein. So a ring is algebraically Gorenstein if the homotopy groups are Gorenstein. And they show that in that case, R is local Gorenstein duality. And that gives already a lot of examples. For example, BUN, the cochange on BUN, because it's a polynomial algebra and it's Gorenstein, then cochange on BUN will satisfy local Gorenstein duality. So for any prime, these local cohomology functors supported at this prime are just a suspension of some injective hole spectrum. So the homotopy is the injective hole of the field, right? Other examples, well, we know that Poincare duality algebras are also Gorenstein, right? Then that means that if you have space X such that, for example, the mod P cohomology is a Poincare duality algebra, then cochange on X is local Gorenstein. So that the basic examples. And then I wanted to show also another example, which is it's very general, that you have a Hoffa space. Remember that a Hoffa space is a space which admits a multiplication and a unit. Yeah. So if you have a Hoffa space such that the cohomology is Noetherian, then work of Breteau-Crespon-Saumell gave explicit description of the cohomology of X with FP coefficients as a tensor as a polynomial algebra, tensor sum quotient of a polynomial algebra, and then one can check from the definition that these cohomology algebras are Gorenstein. So that also gives you a list of examples which are satisfying. For example, the classifying space of a torus. The classifying space of a torus, well, we know it's polynomial, but it's also a Hoffa space. But for example, the 3-connected cover of S3, the classifying, so there are several examples that comes from this family of spaces. So any Hoffa space with Noetherian cohomology algebra, this cohomology algebra by work of Breteau-Crespon-Saumell is Gorenstein, and then in particular the cochange on X will satisfy local Gorenstein duality. And then these are kind of examples that go from polynomial and Poincare duality, and then there are the examples that come from classifying spaces, right? in that case, So, in that case, for example, examples which are not obvious at first, that come from the homotopy theory of classifying spaces. So, that the examples that were introduced by Wilkerson in the 19th, the p-compact groups. So what's a p-compact group? So a p-compact group is a loop space. That means that there is a classifying space such that loops on it is equivalent to X. So it's a loop space such that the mod P cohomology is a finite FP vector space, and that the classifying space is connected and P-complete. And when I say P-complete, I mean P-complete in the senses of Bosfield and Kahn. Right? Examples of P-compact groups, well, compact Lie groups, such that the group of components is a finite P group, just to match with the complete assumptions. So we have a compact Lie group such that the group of components is a finite P group. Then the P completion of G gives an example of a P compact group. So, so if you take the P completion of G, then it turns out to be that it's the loops of the P completion of BG, and this P completion of BG satisfies that it's connected, this is P complete, and that the cohomology of G is FP finite. Because then this gives you an example. These examples are under examples of P-compact groups which do not come from, they're examples of P-compact groups which do not come from this list of examples, which are not P-completions of compact Lie groups. And there are, for example, I think the very first nodes were the Sullivan spheres, and then there are more exotic examples. Okay? And what Dwyer, Greenlees, and Iyengar they show is that cohomology of the cochange of the classifying space of a P-compact group is orientable Gorenstein. And they also describe the shift. The shift is the cohomological dimension of the cohomology of X. I mean, the cohomology of X is a finite vector space, and the cohomological dimension is the dimension of the top non-zero dimension. Okay? So this is that it's orientable Gorenstein. It's proof in the work of Dwyer, Greenlees, and Iyengar. But we want to know about this local Gorenstein duality, whether this goes through to all primes. Okay? And then that's true. And that's the theorem is that if you have a P-compact group, then cochange on Bx satisfies local Gorenstein duality of this shift. So let me make a comment. I mean, when you look at the work of Benson and Carlson, that it's done in the setting of homological algebra. It's not clear which is the how to say. It's not clear how the strategy could go through a more homotopical setting. I mean, the proof is purely algebraic, and then it was not clear from there whether you could go through a homotopical proof of the same statement, right? So all these spectral versions that I've been trying to motivate and explain is giving this homotopical setting for this type of results, right? And but on the one hand, you could also wonder whether you really need the group structure somehow. But going through the family of P-compact groups means that this is not it's a result about finite loop spaces in some sense too, right? That's kind of the philosophy, and I want to make a comment on that, because there is something important, is that in the work of Greenlees, the shift for compact Lie groups is identified always with the dimension of the Lie group, the geometric dimension of the Lie group. In this result, it appears the cohomological dimension of the cohomology of X, which is a finite. And I wanted to make a comment on that because, I mean, it led me to a confusion for a long time. So for a long time, I thought that, okay, let me write the example. So the point is that if you have, as I said, if you have a compact Lie group such that the group of components is a finite P group, you know that the P completion is a P compact group. But it could happen that you have a Lie group which does not fit into that properties, but the P completion is a P compact group, but it's a P compact group represented by another Lie group. I mean, for example, if you take the orthogonal groups at odd primes, they do not satisfy that that the group of components is a finite P group. I mean, it's Z mod 2, right? So for odd primes, the orthogonal groups, they are not in the list of Lie groups which provide examples, but the P completion of the classifying space agrees with the P completion of another Lie group, which is the symplectic SPN. And this one, it satisfies this property. That's what in the work of Ishiguro, he calls them compact Lie groups of P compact type. They are compact Lie groups. Essentially, the property is that they are compact Lie groups such that the cohomology of loops on BG P completed is finite. That's essentially what you need. And in that case, if you take the orthogonal groups and you P complete at odd primes the classifying space, and you look at the cohomology, what you obtain is finite. So since it's finite, it's a P compact group, but it is because it coincides at odd primes with SPN, right? And why I'm saying that is that in that case, the orthogonal groups satisfy local Gorenstein duality at odd primes. The problem, but it's not really a problem, is that the shift does not coincide with the geometrical dimension. The point is that the shift is the cohomological dimension of the loop space, right? So, so that's I wanted to point out here in the theorem that the shift, even for those examples, previously the shifts were always identified with the geometrical dimension of the Lie group. But as soon as you P complete, you land in the world of P compact groups, and in the world of P compact groups, the notion of dimension is the cohomological dimension of the loop space, right? So for example, O2 is Gorenstein of shift 3, right? Not 2 at odd prime, I mean, not 1 at odd primes, but it's Gorenstein nevertheless. So that's something I wanted to point out, but it led to confusion with myself before. So, and so this is the family of, so this theorem, in the case of compact Lie groups, it goes through all compact Lie groups, what they are called of P compact type, right, by Ishiguro. Okay, so what's good about knowing that the P compact groups satisfy local Gorenstein duality and the shift is the cohomological dimension? Well, you can then obtain results of this type if you have a map between classifying spaces of P compact groups. They could be just P completions of compact connected Lie groups, for example, if you feel more comfortable. And I denote the homotopy fiber of this map from X mod I, just imitating the idea of the homogeneous spaces. So, and assume that this homotopy fiber is connected, and that the cohomology is FP finite. So I have this map between classifying spaces of P compact groups, and I know that the homotopy fiber is connected and has finite mod P cohomology. Finite means FP, a finite FP vector space. Not only it's finite type in its dimension, and it's finite. Yeah. Then it satisfies Poincare duality. So the homotopy fiber of maps between classifying spaces of P compact groups, if this homotopy fiber is connected in a FP fiber, it automatically will have Poincare duality. So this is the type of result that you can obtain from knowing that cochange on Bx satisfies this local Gorenstein duality. And the idea of the proof is just perform an ascent technique using unitary groups, right? So the sketch of the proof, I just said it's the existence of very nice maps from BX into unitary groups, classifying species of unitary groups from P-compact groups. It's in a previous work of myself and Cantarero. And then you can perform ascent along this map in the terms of the theorem I told you before. And we know that cochange on BUN. In fact, cochange on BUN is algebraically Gorenstein, then it's local Gorenstein at any, it satisfies local Gorenstein duality, right? And there are a more general context to perform, there is a more general context in which to work all these examples, these homotopical examples. I will be very brief about it. That's the theory of P-local compact groups. So there is a more general setting which includes the examples I just, I didn't say it explicitly, but you can, if you have a finite group, you can perform ascent in the same terms I explained before. So cochange on BG, when G is a finite group, also satisfies local Gorenstein duality, right? And just applying the techniques of the ascent I just described. I mean, the idea is as soon as you have a nice embedding, right? So the more general setups for dealing with these mod P analogs of classifying a species, the theory of P-local compact groups. I will be very brief and very naive to give you an idea of what these objects look like. Okay, so first, the basic objects in this theory are the discrete pictorial groups. Those are the basic objects. And a discrete pictorial group is just a group which fits an extension in which the kernel are copies of the proofer group, which mimics a torus in this P-local setting. And the quotient is a finite P group. So that's a discrete pictorial group, right? And these are going to be the basic objects which we'll be playing with. And with these objects, we'll define a category. So we're going with a fusion system. So I will just, there are some axioms which I will not write down, but just to give you a flavor. So it's a category in which it's a fusion system on a discrete pictorial group S. Is a category in which the objects are all P subgroups, all subgroups of S. They are going to be again discrete pictorial. And the morphisms, well, you can choose the morphisms, right? But you have rules to choose the morphisms in this category. First, you have to take all morphisms which are induced by conjugations in the big group S. You have to take all of those, which is this first point. To take all those objects have to be in your category. And your morphisms have to be group monomorphisms, injections. I mean, this is a subcategory. It is a subcategory of the category of groups. I mean, the morphisms are going to be group homomorphisms. They are not abstract, so they are group homomorphisms. In fact, they are going to be group monomorphisms, and you are forced to take all those induced by conjugations in the fixed S that you have. And composition is composition of group morphisms. And the other property is that every morphism, we know that splits as an isomorphism followed by an inclusion, but this isomorphism has to be in the category again, right? And then there are some axioms that I'm not going to describe, which somehow they mimic or they kind of they try to imitate the properties that a C-low subgroup satisfies in a finite group. Yes, essentially, I'm not going to say more because I will go over time. But these are the fusion system on a discrete pictorial group. And the point is that if you have a compact Lie group has a maximal pictorial subgroup, and there is a way of discretizing somehow this maximal pictorial subgroup to obtain a maximal discrete pictorial subgroup for a compact Lie group. Yeah? So once you have this setup, this category, you can ask yourself the following question. I have this category of groups. Remember when at the beginning, when I told you how Quillen was identifying properties of the cohomology of G in terms of inverse limits of cohomology of subgroups, right? So once you have such a system, you can consider abstractly, if you want, the cohomology of all these groups in this category, and you can look at this inverse limit. You can take the inverse limit over this category that you just described of the cohomology of VP. You have a functor from your category to the category that takes cohomology of VP, and you take the inverse limit. So here you have defined perfectly an algebra. That's not a problem. Right? So this inverse limit, you can ask yourself whether this is the cohomology of anything. Right? If this was a finite group and P would be all P subgroups, the answer is yes, that's the cohomology of G. That's the cohomology of VG. So there is a space, VG, which realizes this inverse limit when you are taking a very specific situation. That's when you take all P subgroups of G, and morphisms, you take only those induced by conjugation in G. That's an example that you can realize. But if you work in this abstract setting in which the morphisms are choosing to imitate conjugations, but you don't have this big supergroup G, and then you can consider this inverse limit. You can ask yourself whether this is the cohomology of anything. Yeah? And I'm being very naive going through all this theory, right? So, and then, for example, if for a compact Lie group, if you take discretizations of p-total subgroups and certain conditions, then you also recover the cohomology of VG by work of several authors. But the question is whether you can, in general, do it, and then the answer is yes. There are all these saturation axioms hidden here that I didn't want to write down, but there is work of Shermack, Oliver, and Levy-Lippmann that describe that say that yes, there is a classifying space for this structure. So this structure, this saturated fusion system and a discrete p-total group, one can associate a space to it, which we'll call the classifying space, in a way that the cohomology of this space is this inverse limit of the cohomology of VP. And in some sense, we abstractly compute some stable elements of something, and then we say, yes, there is a space that its cohomology is exactly these stable elements of that we just constructed abstractly. Right? And then I'm not going to say much, but well, there are all this work of Brotto, Levy, and Oliver for the case in which S is a finite P group, and then you recover VG, but there are other examples which do not come from finite groups. There are exotic examples. And then in the case of P-local compact groups, this framework includes inside this big framework, you can see finite groups, all compact Lie groups with no restriction on the group of components, and more other examples coming from torsion groups, for example, linear torsion groups. So this is a much more big setting, which includes so if you can prove something in this context for P-local compact groups, in particular, you're proving it for finite groups, for compact Lie groups, and other examples, right? So the problem, this is a summary. So the problem here is that I would like to perform ascent in the same conditions I did for previous examples, but it's not known in general that you can construct a nice vibration from the classifying space of this classifying space of this system, this separative fusion system, into a unitary group with nice properties of the fiber, essentially that the cohomology would be Poincare duality. If you could have this, then automatically you would have this local Gorenstein duality sorry, this local Gorenstein duality for those spaces, right? But there is a situation in which it can be done is in the situation for finite. So for P-local finite groups, it's known that there is such a unitary embedding. So it was a previous work of myself with José Cantarero and Lola Morales. And then in that case, at least for the finite situation, you know this, you know that this cochange on BG satisfy this local Gorenstein duality. Okay, so I didn't say anything about the case of the rational case in which we take coefficients in rational case. Well, in that case, essentially, if you have Gorenstein of shift R, I mean, you need simply connected, but in this case, if you have Gorenstein of shift R, then automatically you have this local Gorenstein duality, which is also in our work. But I was concentrated on, well, my favorite example, which are the classifying spaces. Right? And then, yeah, so for this more general setting, you need, you don't have this nice setting for perform ascent. But and then just maybe a thought. I mean, I was thinking that I didn't say anything here about the shift. So if it's a p-local finite group, the shift is 0. Right? In that case, the shift is 0. The same for finite groups. Even the loops, so with that they are not p-compact groups, because when you take the loops of the p-completion, this is not finite. It's very big, right? But the shift is 0, right? In the case of a p-local compact group, there is no, in the case of p-compact groups, you have a notion of dimension. So the dimension of a p-compact group is the cohomological dimension. And that's what appears in the shift. For a finite group, the shift is 0. That's somehow the dimension of a finite group, if you want. So what it's if a p-local, if you could show that the cochange on BG for a p-local compact group is Gorenstein, then you would obtain a number from it, this shift, right? So my feeling, or just, is that this shift could be the dimension of a p-local, because we know that it behaves nicely with vibrations. I mean, it adds in vibration. It has a very nice properties. So if you could get a result saying that cochange of a p-local compact group is Gorenstein, that could give you a number, this shift. And this shift, I think of it as a type of dimension for this object. Okay, so I think I will stop here. Yeah. Okay, so thank you very much.
Thank you, Natàlia, for a nice talk.
I went very fast.
Are there comments, questions?
Yeah, I think I was too fast. Sorry.
So maybe just a question that comes to my mind now that you talk about these dimensions. It's a very interesting idea. But what happens with finite loop spaces?
With finite loop spaces?
Finite loop spaces. If you p-complete, you get an extension of a p-compact group for which you have the theory, and a finite group.
Yeah, let me remind, I think in a work with José Cantarero, we constructed unitary embeddings for finite loop spaces. We have these unitary embeddings. But now I should check. I tend to forget my own work. The problem, you should need some Poincare duality on the fiber. That's an important step. And I think that's what we don't have for this case. No, that's a good point. The problem for p-local finite groups, we managed to show that the homotopy fiber of the unitary embedding, it has this Poincare duality property.
Oh, but these are local. The completion of finite loop space is a p-local compact group.
Yeah, exactly. So I should look, but if you have, it depends on whether this homotopy fiber has this Poincare duality property. But yeah, maybe it's already there and I forgot about it. Yeah, but that's a good point. Yeah, but the unitary embeddings exist. That's part of our work. That But at that time, I was not that concentrated on showing these properties on the fiber. So I should look at it. Yeah, that's a good question.
Thank you.
Yeah.
Any other questions or comments? So if not, we thank our speaker again.
Okay, thank you.
And we continue this afternoon at 3:15.
Okay.